Imagine gravity so strong that a teaspoon of matter weighs as much as Mount Everest, a place where time crawls so slowly that 1 second equals years in the outside universe. Now imagine an object so dense that atoms themselves collapse, creating a form of matter that shouldn't exist. Welcome to the interior of a neutron star, the most extreme gravitational environment in the universe that we can still observe. Today, we're going on a journey to understand what happens to gravity when it's pushed to its absolute limits, where the familiar laws of physics break down and reality becomes stranger than science fiction. If you're hungry for more mind-bending cosmic truths like this one, subscribe to the channel and give a thumbs up. Your support means a lot to me. Now let's begin. Neutron stars are the collapsed cores of massive stars that died in supernova explosions. When a star between 8 and 20 times the mass of our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses in less than a second, crushing matter into the densest form possible without becoming a black hole. What remains is a city-sized sphere of matter so extreme that it challenges our understanding of physics itself. To grasp the mind-bending nature of neutron star gravity, let's start with some numbers that will break your brain. A typical neutron star packs 1.4 times the mass of our Sun into a sphere just 20 kilometers across, about the size of Manhattan. The surface gravity is 200 billion times stronger than Earth's. If you dropped an object from 1 meter above the surface, it would hit at 2,000 kilometers per second, a significant fraction of light speed. But these numbers only hint at the true strangeness inside. As we journey from the surface to the core, gravity doesn't just get stronger, it fundamentally changes how matter, energy, space, and time behave. We're entering a realm where quantum mechanics and general relativity clash, where new forms of matter emerge, and where our equations start to fail. The story of understanding neutron star gravity begins with one of the most brilliant minds in physics, Subramanian Chandrasekhar. In 1930, while sailing from India to England to study at Cambridge, the 19-year-old Chandrasekhar worked out the mathematics showing that stars above a certain mass, now called the Chandrasekhar limit of 1.4 solar masses, must collapse into something denser than a white dwarf. His calculations were met with skepticism and even ridicule from established astronomers like Arthur Eddington, but they laid the foundation for understanding stellar collapse. The theoretical prediction of neutron stars came in 1934 from Walter Baade and Fritz Zwicky, just 2 years after the neutron itself was discovered. They proposed that supernovae could create neutron stars, objects composed almost entirely of neutrons. But it wasn't until 1967 that Jocelyn Bell Burnell, then a graduate student, discovered the first neutron star by detecting regular radio pulses from what we now call pulsars. Modern observations have revealed over 3,000 neutron stars in our galaxy alone. The NICER mission, Neutron Star Interior Composition Explorer, mounted on the International Space Station, uses X-ray timing to map neutron star surfaces and probe their interiors. The LIGO and Virgo gravitational wave detectors have observed neutron star collisions, revealing how these extreme objects behave when gravity pushes them to their breaking point. But to understand what happens to gravity inside a neutron star, we need to think about gravity differently than the simple force that pulls things down we learn in school. Einstein's general relativity reveals that gravity isn't a force at all. It's the curvature of space-time caused by mass and energy. The more mass you pack into a smaller space, the more extreme this curvature becomes. Near a neutron star, space-time is so severely warped that our normal concepts break down. Time dilation becomes extreme, clocks on the surface run about 30% slower than clocks far away. Light paths bend so severely that you could theoretically see the back of your own head. Space itself is dragged around rotating neutron stars in a phenomenon called frame dragging, measured by observing pulsar timing. The surface of a neutron star marks the beginning of our journey into gravitational extremes. Here, gravity is so strong that the escape velocity is about 1/3 the speed of light. The atmosphere, if it exists at all, is compressed into a layer just centimeters thick. Mountains, limited by gravity, can be at most a few millimeters high. Any taller, and gravity would crush them flat. Recent observations by NASA have mapped hotspots on neutron star surfaces, revealing how matter behaves under these extreme conditions. The X-ray light from these hotspots is gravitationally lensed, bent by the star's gravity so severely that we can see parts of the far side. This isn't science fiction, it's observed reality that confirms Einstein's predictions in the strong field regime. But the surface is just the beginning. As we descend into the neutron star, we encounter layers of matter in states that can't exist anywhere else in the universe. The outer crust, perhaps a kilometer thick, consists of a crystalline lattice of heavy nuclei immersed in a sea of electrons. The pressure here is already quadrillions of times greater than at Earth's center. Deeper still, we enter the inner crust, where neutrons begin to drip out of atomic nuclei. This neutron drip occurs at densities around 4 × 10 to the 11th grams per cubic centimeter, about 400 million tons per teaspoon. Here, matter exists in forms with names like nuclear pasta. Sheets, tubes, and bubbles of nuclear matter arranged in ways that minimize energy under extreme pressure. The physics of nuclear pasta is so complex that scientists use supercomputers to model it. Simulations at Indiana University and elsewhere show that these structures might be the strongest material in the universe, with breaking strains 10 billion times greater than steel. This isn't just theoretical. The way pulsars spin down over time suggests their crusts are incredibly rigid, supporting these exotic calculations. As we continue inward, the distinction between individual nuclei disappears. We enter the outer core, where matter becomes a superfluid soup of neutrons with a sprinkling of protons and electrons. Here, densities reach nuclear saturation, about 2.8 × 10 to the 14 grams per cubic centimeter. At this density, neutrons are packed as closely as they are inside atomic nuclei. The superfluid neutron sea in the outer core represents one of the most exotic states of matter in the universe. Superfluidity, the ability to flow without friction, occurs when quantum mechanics dominates over thermal motion. On Earth, we can create superfluids only near absolute zero. Inside neutron stars, the pressure is so extreme that neutrons become superfluid even at temperatures of hundreds of millions of degrees. This isn't just theoretical physics. We observe the effects of neutron superfluidity directly. Pulsar glitches, sudden speed-ups in neutron star rotation, occur when the superfluid interior and the solid crust temporarily decouple and then reconnect. The Vela pulsar, observed continuously since 1969, has glitched over 20 times, each event revealing the strange quantum properties of matter under extreme gravity. But superfluidity is just the beginning of the quantum weirdness. The protons mixed with the neutrons likely form a superconductor, conducting electricity with zero resistance. This creates magnetic fields of unimaginable strength. While Earth's magnetic field is about half a Gauss and a refrigerator magnet is about 100 Gauss, neutron star magnetic fields range from 100 million to 1 quadrillion Gauss. These magnetic fields are so strong they distort atoms themselves. In fields above 10 to the 9th Gauss, the quantum critical field, atoms are stretched into needle-like shapes hundreds of times longer than wide. Chemistry, as we know it, ceases to exist. The magnetic field energy density becomes comparable to the mass energy density of matter itself, warping space-time through its sheer intensity. If you're fascinated by these extreme physics and want to dive deeper into the science of neutron stars, I highly recommend the book Neutron Stars: The Quest to Understand the Zombies of the Cosmos by Katia Moskvich. She brilliantly weaves together the history of neutron star discovery with cutting-edge research, interviewing the scientists who are pushing our understanding of these cosmic monsters. It's the perfect companion to truly grasp how these zombie stars challenge everything we thought we knew about matter and gravity. The link is in the description and pinned on the comments. Now let's continue our journey toward the core. As we descend deeper, approaching densities of 5 times nuclear saturation, we enter truly uncharted territory. Here, the equations of state, the relationships between pressure, density, and temperature become uncertain. We know matter must be there, we can calculate the gravitational field it creates, but we don't know exactly what form it takes. This is where competing theories diverge and our understanding reaches its limits. One possibility is that neutrons break down into their constituent quarks. Neutrons and protons are made of up and down quarks bound together by the strong force. Under extreme pressure, these quarks might become deconfined, creating a quark-gluon plasma similar to what existed microseconds after the Big Bang. If this happens, we'd have a hybrid star, neutron star on the outside, quark star on the inside. The evidence for quark matter in neutron stars is tantalizing but inconclusive. Some neutron stars seem too massive to be supported by neutron degeneracy pressure alone. PSR J0740.62, discovered by the Green Bank telescope, has a mass of 2.17 solar masses, pushing the theoretical limits for pure neutron matter. Either our nuclear physics is incomplete, or something exotic like quark matter provides additional support. Strange quark matter presents an even more exotic possibility. In addition to up and down quarks, strange quarks might appear at extreme densities. Some theories suggest strange quark matter could be the true ground state of matter, more stable than atomic nuclei. If so, neutron stars might convert entirely to strange stars, objects even denser and more bizarre than conventional neutron stars. But gravity inside neutron stars isn't just about density, it's about how that density warps space-time. The Tolman-Oppenheimer-Volkoff equation, the relativistic version of hydrostatic equilibrium, governs the balance between gravity and pressure. Unlike in Newtonian gravity, pressure itself contributes to the gravitational field in general relativity. This creates a vicious cycle. More pressure to support against gravity means stronger gravity, requiring even more pressure. This relativistic effect places an absolute upper limit on neutron star mass. Current observations suggest this limit is around 2.3 solar masses, though the exact value depends on the still uncertain equation of state. Beyond this mass, no amount of pressure can halt collapse, and the neutron star becomes a black hole. The boundary between neutron stars and black holes represents the edge of observable extreme gravity. The space-time geometry inside neutron stars is described by the Schwarzschild metric for non-rotating stars or the Kerr metric for rotating ones. But these are external solutions. Inside the star, we need numerical relativity to solve Einstein's equations. Supercomputer simulations at facilities like the Albert Einstein Institute show how space-time curves and twists throughout the stellar interior. At the center of a neutron star, space-time curvature reaches extremes second only to black holes. The metric components, the mathematical description of space-time geometry, deviate dramatically from flat space. Time dilation approaches factors of 2 or more, meaning time at the center passes half as fast as at infinity. Space is compressed and stretched in ways that would spaghettify any normal matter. The central density might reach 10 times nuclear saturation or more, over 1 billion tons per cubic centimeter. At these densities, our understanding of particle physics breaks down. We need a theory of quantum gravity to properly describe matter and spacetime at these scales, but such a theory remains elusive. Neutron star cores probe physics at energies we can't reach in any terrestrial experiment. Recent gravitational wave observations provide new windows into neutron star interiors. The GW170817 event, the collision of two neutron stars observed by LIGO and Virgo, revealed how matter behaves when extreme gravity meets extreme gravity. The gravitational wave signal encoded information about the star's deformability, constraining the equation of state and revealing that neutron star matter is relatively soft, more easily compressed than some theories predicted. The Kilonovae that followed GW170817, observed by telescopes worldwide, showed the creation of heavy elements like gold and platinum. The extreme gravity during merger doesn't just deform matter, it enables nuclear processes impossible anywhere else, forging half the elements heavier than iron. We are literally made of atoms created in the extreme gravity of colliding neutron stars billions of years ago. Multi-messenger astronomy, combining gravitational waves, electromagnetic signals, and neutrinos, is revolutionizing our understanding of neutron star gravity. The NICE mission has measured neutron star radii to within hundreds of meters, constraining how matter responds to extreme gravity. Every observation adds pieces to the puzzle of what happens when gravity overwhelms all other forces. At the heart of a neutron star lies one of the greatest mysteries in physics, the intersection of quantum mechanics and general relativity. These two pillars of modern physics, each spectacularly successful in their own domains, clash violently in the extreme conditions we're exploring. Understanding gravity inside neutron stars requires navigating this theoretical battlefield where our equations begin to fail and new physics might emerge. Quantum mechanics governs the microscopic world with probabilistic laws and uncertainty principles. General relativity describes gravity as smooth, continuous space-time curvature. In most of the universe, these theories politely ignore each other. Quantum effects are negligible at large scales, and gravity is weak at quantum scales. But inside neutron stars, we can't ignore either. Quantum pressure supports the star against gravitational collapse, while gravity is strong enough to affect quantum behavior. The Pauli exclusion principle, a cornerstone of quantum mechanics, states that no two fermions, particles like neutrons, protons, and electrons, can occupy the same quantum state. This creates degeneracy pressure, a purely quantum mechanical effect that has nothing to do with temperature. In white dwarfs, electron degeneracy pressure provides support. In neutron stars, neutron degeneracy pressure takes over, but at much higher densities where relativistic effects become crucial. At neutron star densities, particles are squeezed so close together that their quantum wave functions overlap significantly. The Heisenberg uncertainty principle tells us that confining particles to smaller spaces gives them higher momentum. In neutron star cores, neutrons are confined to spaces smaller than their Compton wavelength, making them ultra-relativistic. Their kinetic energy approaches or exceeds their rest mass energy. This is where things get weird. In classical physics, particles are particles and waves are waves. In quantum mechanics, everything exhibits wave-particle duality. In relativistic quantum mechanics, the situation becomes even stranger. Particles can be created and destroyed. Virtual particles pop in and out of existence, and the vacuum itself seethes with quantum fluctuations. Inside neutron stars, these effects aren't tiny corrections, indeed, they're dominant. The quantum vacuum inside a neutron star is far from empty. The extreme gravitational field polarizes the vacuum, creating a sea of virtual particle-antiparticle pairs. These virtual particles affect real particles, modifying their properties in ways we're still trying to understand. The strong force, electromagnetic force, and weak force all behave differently in this modified vacuum, potentially creating new phases of matter. Color superconductivity represents one such exotic phase. At extreme densities, quarks might pair up like electrons in a superconductor, but with color charge instead of electric charge. This creates a state where the strong force exhibits fundamentally different properties. Some theories suggest color superconducting matter could exist in neutron star cores, creating regions where our normal understanding of nuclear physics breaks down. The equation of state, the relationship between pressure, density, and temperature, becomes incredibly complex when quantum effects dominate. Unlike ideal gases where pressure is proportional to temperature, degenerate matter has pressure even at absolute zero. This zero-point pressure arises from quantum mechanics and increases with density following power laws that depend on whether particles are relativistic or non-relativistic. But here's where gravity throws another wrench into the works. In general relativity, pressure itself gravitates. This seems counterintuitive. How can pressure create gravity? The answer lies in Einstein's equations, where the source of gravity is the stress-energy tensor, which includes not just mass energy, but also pressure and momentum flux. In neutron stars, the pressure required to support against gravity becomes so large that it significantly adds to the gravitational field. This creates a catastrophic feedback loop unique to general relativity. More pressure means stronger gravity, which requires even more pressure to balance, which creates even stronger gravity. This runaway process places an absolute limit on how massive a neutron star can be before it must collapse to a black hole. The Chandrasekhar limit for white dwarfs has a relativistic analog for neutron stars, the Tolman-Oppenheimer-Volkoff limit. Recent calculations using advanced nuclear physics and general relativity place this maximum mass around 2.3 solar masses, though the exact value depends on the uncertain equation of state. The discovery of PSR J09520607, a millisecond pulsar with a mass of 2.35 solar masses within uncertainties, pushes right up against this limit, suggesting nature creates neutron stars as massive as theoretically possible. The speed of sound in neutron star matter provides another constraint where quantum mechanics meets relativity. In any medium, sound waves can't travel faster than light. This is a fundamental requirement of causality. But in extremely dense matter, the speed of sound approaches significant fractions of light speed. Some equations of state predict sound speeds exceeding 70% of light speed in neutron star cores. This high sound speed has observable consequences. When neutron stars vibrate, and they do in modes called oscillations, these vibrations propagate at the sound speed. The frequencies of these oscillations, potentially detectable in X-ray observations, encode information about the interior structure. Future telescopes might use Asteroseismology to probe neutron star interiors, just as helioseismology reveals the Sun's interior. Quantum chromodynamics, QCD, the theory of the strong force, predicts phase transitions at extreme densities. Just as water transitions from liquid to gas at the boiling point, nuclear matter might transition to quark matter at some critical density. This transition could be smooth or sudden, potentially creating mixed phases where bubbles of quark matter coexist with hadronic matter. The Columbia University lattice QCD calculations suggest these phase transitions occur at temperatures and densities achieved in neutron star cores, but lattice QCD can't yet handle the high-density, low-temperature regime relevant to neutron stars. We're forced to use models and extrapolations, each with different predictions for where transitions occur and what new phases emerge. Superfluidity and superconductivity in neutron star matter arise from quantum many-body effects. When neutrons form Cooper pairs, they create a macroscopic quantum state extending throughout the star. This isn't just ordinary superfluidity, it's relativistic superfluidity in curved spacetime, a regime no Earth experiment can probe. The dynamics of these quantum fluids in strong gravity remain poorly understood. The intersection of quantum mechanics and gravity might even create new particles. Some theories predict axions, hypothetical particles solving the strong CP problem in particle physics, could be produced in neutron star cores. These axions would stream out, carrying away energy and affecting the star's cooling rate. Observations of neutron star temperatures over time constrain these exotic possibilities. The extreme gravity inside neutron stars doesn't hide quietly. It announces itself through spectacular phenomena visible across the universe. Every observation we make of these cosmic laboratories reveals another facet of how gravity behaves when pushed to its limits. From lighthouse-like pulsar beams to catastrophic starquakes, from X-ray bursts to gravitational waves, neutron stars are constantly teaching us about physics in the strong field regime. Pulsars, discovered by Jocelyn Bell Burnell in 1967, were the first evidence that neutron stars actually exist. These cosmic lighthouses sweep beams of radiation across space with clockwork precision. The Crab pulsar, remnant of a supernova observed by Chinese astronomers in 1054 CE, rotates 30 times per second. Each rotation represents the entire star, a mass greater than our Sun, spinning faster than a kitchen blender. But how does extreme gravity create these beams? The answer lies in the interplay between gravity, magnetic fields, and plasma physics. Neutron stars have the strongest magnetic fields in the known universe, typically 1 trillion times stronger than Earth's. These fields are frozen into the star during collapse, compressed, and amplified by conservation of magnetic flux. The result is a magnetic field so strong it would rip the iron from your blood at a distance of 1,000 kilometers. These magnetic fields channel charged particles along field lines, accelerating them to near light speed. As these particles spiral along the field lines, they emit synchrotron radiation, electromagnetic waves created by accelerating charges. But here's where gravity enters the picture. The particles are accelerated not just by electromagnetic forces, but by the gravitational field itself. Near the neutron star surface, gravity is so strong that in falling particles reach significant fractions of light speed. The pulsar mechanism requires several ingredients that only extreme gravity can provide. First, the compactness. Pulsars work because neutron stars pack immense mass into tiny volumes, creating steep gravitational gradients. Second, the rapid rotation. Conservation of angular momentum during stellar collapse spins neutron stars up to incredible speeds. Third, the stability. Despite their extreme conditions, neutron stars are remarkably stable, maintaining precise rotation periods for millions of years. Millisecond pulsars represent the extreme end of neutron star rotation. PSR J1748-2446 ED spins 716 times per second. Its equator moves at 24% of light speed. At this rotation rate, The star is near the breakup limit where centrifugal force would overcome gravity. The surface gravity, normally 200 billion times Earth's, is significantly reduced at the equator by rotation. These rapid rotations reveal how matter behaves under extreme gravity. The neutron star deforms into an oblate shape, wider at the equator than the poles. This deformation is tiny, perhaps a few percent, but measurable through its effect on the pulsar's emission. The shape depends on the equation of state, giving us another probe of ultra-dense matter. Pulsar timing has revealed phenomena that showcase extreme gravity. The double pulsar system PSR J07373039AB consists of two pulsars orbiting each other every 2.4 hours. This system is a gravitational laboratory par excellence. We observe periastron advance. The orbit's orientation rotates by 17 degrees per year, compared to Mercury's 43 arcseconds per century. This dramatic effect arises from the extreme space-time curvature near the neutron stars. Even more remarkably, we observe geodetic precession in this system. The spin axes of the pulsars precess around the total angular momentum vector due to space-time dragging. This effect, predicted by general relativity, causes the pulsar beams to sweep across different parts of the sky over time. We're literally watching space-time twist and drag around these massive objects. Gravitational waves from neutron stars provide the most direct probe of extreme gravity. The GW177817 event, detected by LIGO and Virgo, came from two neutron stars spiraling together and merging. In the final seconds, these stars orbited each other hundreds of times per second, moving at significant fractions of light speed. The gravitational waves encode precise information about the masses, spins, and internal structure of the stars. The merger itself represents gravity at its most extreme. As the stars touch, tidal forces rip them apart in milliseconds. Matter, compressed beyond nuclear density, suddenly finds itself in a lower pressure environment, causing violent oscillations. Some matter is ejected at 20 to 30% of light speed, while the rest collapses into either a massive neutron star or a black hole. The electromagnetic counterpart to GW170817, observed by over 70 telescopes worldwide, revealed the Kilonova. This explosion, powered by radioactive decay of freshly synthesized heavy elements, confirmed that neutron star mergers create much of the universe's gold, platinum, and other heavy elements. The extreme gravity doesn't just deform matter, it enables nucleosynthesis processes impossible anywhere else. X-ray observations reveal another facet of extreme gravity, accretion. Many neutron stars have companion stars from which they steal matter. This matter spirals inward through an accretion disk, heating to millions of degrees. When it finally reaches the neutron star surface, it releases its gravitational potential energy in a burst of X-rays. A marshmallow dropped onto a neutron star would release energy equivalent to 1,000 Hiroshima bombs. Type Y, X-ray bursts occur when accreted hydrogen and helium build up on the surface until they ignite in thermonuclear explosions. These bursts reveal the surface gravity directly. We can measure how much the X-ray light is gravitationally redshifted as it climbs out of the gravitational well. Observations by NICER have measured redshifts of 20 to 30%, confirming the extreme surface gravity. Magnetars, neutron stars with magnetic fields exceeding 10 to the 14th Gauss, show how extreme gravity couples with extreme magnetism. These fields are so strong that quantum electrodynamics predicts vacuum birefringence. Empty space acts like a crystal, splitting light into two polarization modes. This effect, recently confirmed in observations of the magnetar RX J1856-53754, shows how gravity and electromagnetism intertwine in the strong field regime. Starquakes on magnetars release more energy in 1/10 of a second than our Sun emits in 100,000 years. The December 27, 2004 event from SGR 1806-20 was so powerful it measurably affected Earth's ionosphere from 50,000 light-years away. These quakes occur when magnetic stress overcomes the neutron star's incredible crustal strength, cracking the surface and reconfiguring the magnetic field. Inside a neutron star, matter and spacetime engage in an intricate dance where each partner influences the other in ways that challenge our understanding of physics. The matter tells spacetime how to curve through Einstein's field equations, while the curved spacetime tells matter how to move. But at neutron star densities, this relationship becomes so extreme that new phenomena emerge, phenomena that exist nowhere else in the observable universe. Frame dragging, also known as the lens-Thirring effect, demonstrates how rotating mass literally drags spacetime around with it. Near Earth, this effect is tiny. Gravity Probe B needed ultra-precise gyroscopes to measure it. But around rapidly rotating neutron stars, frame dragging becomes dominant. Space itself swirls around the star like honey around a spinning spoon, forcing any nearby matter to rotate with it. In the ergosphere of a rotating neutron star, the region where frame dragging exceeds the speed of light, strange things happen. Nothing can remain stationary relative to distant stars. Everything must rotate with the space-time flow. This isn't just theoretical, we observe its effects in accretion disks around neutron stars, where matter is forced into specific orbital patterns by the dragged space-time. The innermost stable circular orbit, ISCO, marks where gravity becomes so strong that stable orbits are impossible. For a non-rotating neutron star, the ISCO is at 3 times the Schwarzschild radius, but rotation changes everything. A neutron star spinning at 700 times per second has its ISCO much closer, allowing matter to orbit in regions of extreme gravity that would be unstable around slower rotators. Recent simulations by groups at the Max Planck Institute for Gravitational Physics show how matter behaves near the ISCO. Particles don't just spiral inward, they exhibit complex oscillations called epicycles, tracing flower-like patterns as they orbit. These patterns encode information about the space-time geometry, potentially observable in the flickering X-ray light from accreting neutron stars. The plunging region inside the ISCO represents gravitational freefall. Matter here has passed the point of no return, doomed to hit the neutron star surface within milliseconds. But during this brief plunge, it experiences some of the strongest gravitational fields in the universe outside black holes. Time dilation becomes extreme, length contraction approaches its limits, and tidal forces threaten to tear apart anything held together by electromagnetic forces. Tidal forces around neutron stars are strong enough to disrupt atomic structure. The gravitational gradient, the difference in gravitational pull between your head and feet if you were falling feet first, would stretch you into a stream of particles long before you reached the surface. This spaghettification isn't just science fiction. We observe it happening to asteroids and comets that venture too close to neutron stars. But inside the neutron star, where matter is already crushed beyond recognition, tidal forces play a different role. They create differential rotation, different layers rotating at different speeds. This differential rotation winds up magnetic field lines, potentially powering the star's electromagnetic emission. It also creates viscosity in what would otherwise be a perfect superfluid, allowing angular momentum transport that affects the star's evolution. The R-mode instability demonstrates how gravity couples with fluid dynamics in neutron stars. These are oscillation modes driven unstable by gravitational radiation. As the star oscillates, it emits gravitational waves that carry away angular momentum. Under certain conditions, this creates a runaway process that could spin down the star or even tear it apart. The fact that we observe rapidly rotating neutron stars suggests either that viscosity damps these instabilities or that our understanding is incomplete. Mountains on neutron stars showcase the battle between matter's strength and gravity's pull. On Earth, mountains can be kilometers high because rock can support itself against our modest gravity. On neutron stars, the breaking strain of the crustal lattice limits mountains to millimeters. Yet these tiny deformations are crucial. A millimeter-high mountain on a rapidly rotating neutron star creates a time-varying quadrupole moment that emits continuous gravitational waves. And if you think millimeter-high mountains that can create gravitational waves are bizarre, wait until you hear about the other impossible objects lurking in our universe. From planets that rain glass sideways to stars older than the universe itself, I've compiled the most mind-bending cosmic phenomena in my video called 54 Things That Shouldn't Exist in Space, But Do. These objects challenge our understanding of physics just like neutron stars do, proving that reality is far stranger than our theories predict. The link is in the description below and pinned on the card above. Now let's continue with how these tiny mountains are revealing neutron star secrets. The search for continuous gravitational waves from neutron stars is ongoing. LEGO and Virgo have placed upper limits on mountain heights for known pulsars, constraining the breaking strain of neutron star crusts. These limits suggest the crust is incredibly rigid, perhaps the strongest material in the universe, yet still deformable enough to create observable effects. Glitches in pulsar rotation reveal the complex interplay between superfluid and normal matter under extreme gravity. During a glitch, the pulsar suddenly spins faster, then gradually returns to its normal spin-down rate. This happens when the superfluid interior, which rotates independently of the crust, suddenly transfers angular momentum to the crust through vortex unpinning events. The Vela pulsar has glitched over 20 times since observations began, always with remarkably similar characteristics. Each glitch releases about 10 to the 43 ergs of energy, equivalent to the sun's output over several days, in a fraction of a second. These events give us windows into the neutron star interior, revealing superfluid dynamics in gravitational fields 200 billion times stronger than Earth's. Thermonuclear bursts on neutron star surfaces demonstrate how gravity affects nuclear reactions. When accreted hydrogen and helium reach critical density and temperature, they ignite in runaway fusion. But unlike stellar fusion, which is regulated by thermal pressure, neutron star surface fusion occurs at fixed gravitational pressure. The burning front propagates around the star in seconds, visible as Type 1 X-ray bursts. Some neutron stars show superbursts, rare but enormous thermonuclear explosions lasting hours instead of seconds. These might involve carbon fusion deeper in the accumulated ocean of accreted matter. The energy release temporarily doubles the star's luminosity, creating a natural experiment in how extreme gravity affects nuclear burning. Photospheric radius expansion during these bursts reveals gravity's grip on light itself. When the burst luminosity exceeds the Eddington limit, where radiation pressure equals gravitational pull, the photosphere lifts off the surface. We observe the apparent radius increase, then contract as the burst subsides. By measuring this expansion against the gravitational redshift, we can determine both the star's mass and radius. The equation of state of ultra-dense matter fundamentally depends on gravitational effects. At low densities, pressure comes mainly from particle motion, but at neutron star densities, gravitational interaction energy becomes comparable to rest mass energy. Particles don't just orbit in a gravitational field, they help create that field, leading to non-linear feedback that modifies the equation of state itself. When neutron stars collide, the universe witnesses gravity at its most violent and spectacular. These cosmic crashes don't just bend space-time, they create tsunamis in the fabric of reality itself, sending gravitational waves racing across billions of light-years. The final moments before merger showcase physics so extreme that our equations struggle to keep up, and new states of matter flash into existence for mere milliseconds before vanishing forever. The approach to merger is deceptively gentle at first. Two neutron stars, locked in a gravitational embrace, spiral around each other for millions of years. They lose energy through gravitational wave emission, a process so slow that the orbit shrinks by just millimeters per year initially. But this gradual in-spiral is like a cosmic time bomb storing energy for an eventual catastrophic release. Einstein predicted gravitational waves in 1916, but it took a century to detect them. The reason is their incredible weakness. Even the violent collision of neutron stars creates space-time distortions smaller than the width of a proton by the time they reach Earth. LIGO's laser interferometers can measure distance changes of 10 to the negative 18 meters, equivalent to measuring the distance to the nearest star to the width of a human hair. As the neutron stars spiral closer, the process accelerates exponentially. In the final minute, they complete more orbits than in the previous million years. The gravitational wave frequency sweeps upward from 10 Hz to over 1000 Hz, an ascending chirp that encodes precise information about the star's masses, spins, and internal structure. This chirp is gravity singing its most extreme song. The tidal deformation in the final orbits reveals the neutron star equation of state. Unlike black holes, which are perfect spheres or oblate spheroids if rotating, neutron stars can be stretched and squeezed. The more deformable they are, the more energy goes into tidal heating rather than gravitational waves. LIGO and Virgo measure this deformability through subtle changes in the gravitational wave phase evolution. At about 100 kilometers separation, when the stars are orbiting hundreds of times per second, tidal forces begin disrupting the stellar surfaces. Matter streams between the stars, creating bridges of nuclear density material experiencing gravitational fields that vary by factors of 2 over distances of meters. This matter doesn't just fall, it's stretched, compressed, and heated to billions of degrees. The moment of contact triggers chaos. Two objects, each supporting matter at nuclear density through quantum degeneracy pressure, suddenly interpenetrate. The collision region experiences densities exceeding anything in the isolated stars, perhaps reaching 10 times nuclear saturation. At these densities, matter might undergo phase transitions to quark matter, or even more exotic states that exist for microseconds before the system either collapses or explodes. Computer simulations of neutron star mergers push supercomputers to their limits. Groups at Caltech, the Albert Einstein Institute, and Japanese institutions use millions of CPU hours to evolve Einstein's equations coupled with nuclear physics, magnetic fields, and neutrino radiation. Each simulation covers just seconds of physical time but reveals physics spanning from quantum to cosmic scales. The merger outcome depends critically on the total mass. If the combined mass exceeds the maximum neutron star mass, about 2.3 solar masses, the remnant collapses to a black hole within milliseconds. But this isn't a simple implosion. It's a complex dance where centrifugal forces from rapid rotation temporarily support a hypermassive neutron star before gravity inevitably wins. During this hypermassive phase, the remnant oscillates violently. These oscillations emit gravitational waves at frequencies of 2 to 4 kHz, too high for current LIGO sensitivity, but potentially detectable by next-generation observatories like the Einstein telescope. The frequency of these oscillations directly encodes the equation of state of matter at the highest densities in the universe. If the total mass is low enough, a stable neutron star survives, but it's unlike any neutron star formed in supernovae. The merger product is differentially rotating, spinning faster in the center than at the surface, and pervaded by magnetic fields amplified to 10 to the 16 Gauss or higher. This ultramagnetized, differentially rotating remnant might be the birth of a magnetar. The matter ejected during merger, at 1 to 5% of the total mass, undergoes rapid neutron capture, our process, nucleosynthesis. In less than a second, this matter creates gold, platinum, uranium, and other heavy elements. The radioactive decay of these freshly synthesized elements powers a kilonova, an optical and infrared transient that can outshine a galaxy for days. The GW 170817 event provided our first direct observation of this process. The Kilonova AT2017 GFO was observed by telescopes worldwide, confirming that neutron star mergers are cosmic foundries for heavy elements. The amount of gold produced in this single event exceeded the mass of Earth. Every gold atom in your jewelry was likely forged in the extreme gravity of colliding neutron stars billions of years ago. The neutrino emission during merger is staggering, about 10 to the 53 neutrinos carrying 10% of the total mass energy. These neutrinos are produced by weak interactions as protons and neutrons convert back and forth under extreme conditions. While most stream freely into space, some are trapped by the dense matter, creating a neutrinosphere analogous to a star's photosphere. Jets launched from merger remnants might power short gamma-ray bursts, the most luminous explosions in the universe after the Big Bang. These jets must punch through the merger ejector, creating a cocoon of shocked material. How a jet forms in this chaotic environment, reaching Lorentz factors exceeding 100 while maintaining collimation, remains an active area of research. The magnetic field evolution during merger is spectacular. Kelvin-Helmholtz instabilities at the shear layer between the merging stars amplify fields exponentially. Magneto-rotational instabilities in the remnant disk further boost field strength. Within milliseconds, magnetic fields reach strengths where magnetic pressure rivals matter pressure, fundamentally altering the dynamics. Black hole formation from neutron star merger isn't instantaneous. The collapse might stall at nuclear density, bounce, and undergo multiple oscillations before finally succumbing to gravity. During this process, matter experiences the full range of densities from nuclear to infinite, potentially passing through every possible phase of quantum chromodynamics. At the very center of a neutron star, we reach the frontier of human knowledge, a place where our most fundamental theories of physics clash and our equations become uncertain. Here, at densities exceeding 10 times nuclear saturation, matter exists in forms we can barely imagine, let alone calculate. The core is a quantum battleground where the strong force, gravity, and quantum mechanics fight for dominance, potentially creating states of matter that exist nowhere else in the observable universe. The density at the exact center might reach 1 times 10 to the 15 grams per cubic centimeter. That's 1 followed by 15 zeros. To put this in perspective, a sugar cube of this material would weigh more than all of humanity combined. At these densities, individual particles lose their meaning. Quarks and gluons, normally confined inside protons and neutrons, might roam freely in a quark-gluon plasma, similar to what existed microseconds after the Big Bang. But this isn't the quark-gluon plasma we create in particle accelerators. At the relativistic heavy ion collider at Brookhaven, We smash gold nuclei together to create temperatures of 4 trillion degrees, hot enough to melt protons and neutrons into quark soup. Neutron star cores achieve similar densities but at relatively cool temperatures of only hundreds of millions of degrees. This cold, dense quark matter, if it exists, would have properties utterly unlike the hot quark-gluon plasma. Color superconductivity might emerge in this exotic environment. Just as electrons form Cooper pairs in ordinary superconductors, quarks might pair up using the strong force. But unlike electromagnetic superconductivity, color superconductivity involves the pairing of particles that carry color charge, the strong force equivalent of electric charge. This creates a phase of matter where the strong force itself becomes superconducting. The color flavor locked phase represents the most exotic possibility. In this state, quarks of all 3 colors, red, green, blue, and all 3 light flavors, up, down, strange, participate in a complex pairing pattern. This phase would be electromagnetically neutral and might be absolutely stable, more stable than atomic nuclei. If so, neutron stars might convert entirely to strange quark stars over time. Recent lattice QCD calculations on supercomputers provide hints about these phase transitions. The Riken BNL Research Center and other facilities use millions of CPU hours to solve quantum chromodynamics equations on discrete spacetime grids. But these calculations work best at high temperature and struggle with the cold, dense regime of neutron star cores. We're essentially flying blind in the most extreme regions. Hyperons, baryons containing strange quarks, almost certainly appear at high densities. The lambda, sigma, and Xi particles should emerge when the Fermi energy of neutrons exceeds their mass difference. This hyperon puzzle creates a problem. Hyperons soften the equation of state, reducing the maximum neutron star mass below what we observe. Either our nuclear physics is wrong, or something prevents hyperon formation. One solution might be 3 body forces, interactions involving 3 particles simultaneously rather than just pairs. These forces, poorly understood even in normal nuclei, become crucial at high density. They might stiffen the equation of state enough to support 2 solar mass neutron stars even with hyperons present. But calculating 3 body forces from first principles remains beyond our current capabilities. The Pastor phase near the core crust boundary showcases matter's creativity under extreme conditions. Here, competition between nuclear attraction and Coulomb repulsion creates complex geometries. Nuclei merge into rods, spaghetti, rods connect into sheets, lasagna, sheets develop holes, Swiss cheese, and eventually the geometry inverts with nuclear matter surrounding tubes and bubbles of neutron gas. These Pastor phases aren't just theoretical curiosities. They affect neutrino transport during supernovae and neutron star cooling. The complex geometry scatters neutrinos, affecting how quickly newly formed neutron stars lose heat. Observations of neutron star temperatures over time constrain the properties of nuclear Pastor, though uncertainties remain large. Superfluidity in the core involves multiple species. Neutron singlet pairing occurs in the S-wave channel at lower densities, while triplet pairing in the P-wave channel dominates at higher densities. Proton singlet pairing creates a superconductor. These different superfluid phases have different critical temperatures and gap structures, creating a complex phase diagram that varies with radius. The superfluid vortices that thread through neutron star cores are unlike anything on Earth. These quantum tornadoes have cores just femtometers wide, but extend for kilometers. In a neutron star spinning at hundreds of hertz, about 10 to the 19 vortices thread through the core, each carrying 1 quantum of circulation. The interaction between these vortices and the stellar crust drives pulsar glitches. Magnetic flux tubes in the superconducting core are equally exotic. These tubes carry magnetic fields of 10 to the 15 Gauss or higher, confined to regions nanometers wide. The interaction between magnetic flux tubes and superfluid vortices creates a complex dynamical system that might explain magnetar flares and other high-energy phenomena. Dark matter might accumulate in neutron star cores attracted by the extreme gravity. If dark matter consists of WIMPs, weakly interacting massive particles, they would sink to the center over millions of years. Their annihilation could provide additional heating, affecting neutron star cooling curves. Some models suggest dark matter accumulation could even trigger collapse to black holes. Axions, hypothetical particles solving the strong CP problem, might be produced copiously in neutron star cores. These ultralight particles would stream out, carrying energy and affecting cooling rates. The non-detection of excessive cooling in neutron stars places constraints on axion properties, contributing to particle physics beyond the standard model. The possibility of quark nuggets, stable chunks of strange quark matter, adds another layer of complexity. If strange matter is absolutely stable, neutron stars might contain quark matter cores surrounded by hadronic mantles. The interface between phases would be a discontinuity where density jumps dramatically, potentially observable through asteroseismology. Preon stars represent an even more speculative possibility. If quarks and leptons are themselves composite, made of more fundamental preons, then extreme pressure might liberate these constituents. A preon star would be even denser than a quark star, pushing right up against the black hole limit. While purely hypothetical, such objects would revolutionize our understanding of particle physics. Neutron stars are born in the fires of supernovae at temperatures exceeding 100 billion degrees, about 10,000 times hotter than the Sun's core. But from the moment of their birth, they begin a long, slow, cooling process that reveals the physics of matter under extreme gravity. This cooling isn't just heat radiating into space, it's a complex interplay of neutrino emission, superfluidity, and exotic particles that turns each neutron star into a cosmic laboratory for extreme physics. In the first few seconds after formation, neutrinos dominate everything. The newly formed proto-neutron star is so hot and dense that photons are trapped, but neutrinos stream out freely, carrying away 99% of the gravitational binding energy. In those first seconds, a neutron star emits about 10 to the 53 neutrinos, more neutrinos than there are stars in the observable universe. The neutrino luminosity during this phase exceeds 10 to the 52 ergs per second, outshining the entire electromagnetic output of all stars in the observable universe combined. This tremendous energy loss cools the star from 100 billion degrees to about 10 billion degrees in just 10 seconds. It's the fastest cooling rate of any object in the universe. But after this dramatic beginning, the cooling slows dramatically. The star becomes transparent to neutrinos and the emission rate drops. Now the cooling is governed by neutrino emission from the interior and photon radiation from the surface. The competition between these two cooling mechanisms depends on the star's mass, composition, and the presence of exotic matter. The URC process, named whimsically after a casino in Rio de Janeiro where money disappeared quickly, dominates neutrino cooling in the core. In the direct Urca process, neutrons convert to protons by emitting electrons and antineutrinos, then protons capture electrons to convert back to neutrons, emitting neutrinos. This cycle efficiently converts thermal energy to neutrinos that escape the star. But the direct Yuaka process only operates if the proton fraction exceeds about 11%, which occurs only in massive neutron stars or those with exotic matter. Less massive stars cool through the modified Yuaka process, which involves a spectator nucleon and is about 1,000,000 times less efficient. This dramatic difference means neutron star cooling rates encode information about their internal composition. Observations by the Chandra X-ray Observatory and XMM Newton have measured surface temperatures of dozens of neutron stars with known ages. Young neutron stars like the one in Cassiopeia A, only 330 years old, glow at about 2 million degrees. Ancient millisecond pulsars, billions of years old, have cooled to below 100,000 degrees, still hotter than most stellar surfaces. The cooling curve, temperature versus age, isn't smooth. Some neutron stars are too cold for their age, suggesting enhanced cooling from exotic processes. Others are surprisingly hot, indicating heating mechanisms we don't fully understand. The neutron star in Cassiopeia A has cooled by 4% in just 10 years of observations, suggesting rapid cooling that might indicate a superfluid transition in real time. Superfluidity dramatically affects cooling rates. When neutrons form Cooper pairs below the critical temperature, the heat capacity drops suddenly. This is similar to how liquid helium's heat capacity changes at the superfluid transition, but occurring at hundreds of millions of degrees instead of near absolute zero. The pairing also suppresses neutrino emission, creating a complex interplay between cooling and superfluidity. The critical temperature for superfluidity depends on density and varies throughout the star. As the star cools, different regions become superfluid at different times, creating a complex cooling history. Some models predict that the entire core becomes superfluid within thousands of years, while the inner crust might take millions of years to transition. Magnetic field decay provides additional heating that fights against cooling. The ultra-strong magnetic fields in neutron stars aren't stable. They evolve through ohmic dissipation and Hall drift. As magnetic field lines reconnect and decay, they heat the crust. In magnetars, this heating can be so intense that it dominates over cooling, keeping the surface hot for millions of years. Accretion from companion stars or the interstellar medium can also heat neutron stars. Even tiny amounts of matter falling onto the surface release enormous gravitational energy. A kilogram of matter dropping onto a neutron star releases about 20% of its rest mass as energy, more efficient than nuclear fusion. This accretion heating can rejuvenate old, cold neutron stars, making them shine again. Dark matter capture and annihilation might provide exotic heating. If dark matter particles accumulate in the neutron star core and annihilate, they would provide a heat source that grows over time. Some models suggest this could keep neutron stars warmer than expected for their age, though current observations don't require dark matter heating. The atmosphere of a neutron star, though only centimeters thick, crucially affects what we observe. This ultra-thin layer moderates between the million-degree interior and the vacuum of space. Hydrogen atmospheres, even layers just atoms thick, can significantly affect the spectrum, making the star appear cooler than its actual surface temperature. Recent observations have revealed hotspots on neutron star surfaces. NITA's observations of PSR J030+0451 showed that these hotspots aren't at the magnetic poles as expected, but offset in complex patterns. These spots, where magnetic field lines channel particles to heat the surface, create temperature variations that encode information about the magnetic field geometry. The cooling of magnetars is particularly complex. Their ultra-strong magnetic fields affect thermal conductivity, creating temperature inversions where the surface is hotter than layers beneath. Magnetic field decay can trigger sudden heating events, observed as outbursts, where the X-ray luminosity increases by factors of hundreds. Quark matter cores, if they exist, would dramatically alter cooling rates. The quark direct Urca process is even more efficient than the nucleon version, potentially cooling stars in years rather than millions of years. The absence of extremely rapid cooling in young neutron stars places constraints on quark matter, suggesting it either doesn't exist or forms only in the most massive neutron stars. The photon luminosity from the surface follows the Stefan-Boltzmann law, but with a twist. The extreme surface gravity causes gravitational redshift, reducing the observed temperature by about 30%. Time dilation means we observe the cooling happen slower than it occurs on the neutron star surface. These relativistic corrections are essential for comparing theory with observations. Pulsar wind nebulae powered by the neutron star's rotation provide another probe of cooling. As the star spins down, rotational energy heats the surface through various mechanisms. The balance between spin-down heating and cooling affects the surface temperature evolution, particularly for young pulsars with strong spin-down rates. Neutron stars are the universe's gift to physicists. Natural laboratories where conditions impossible to create on Earth reveal truths about the fundamental nature of reality. Every observation of these extreme objects teaches us something new about how matter, energy, space, and time behave when pushed beyond all terrestrial limits. They're testing grounds for theories we could never verify otherwise, and they keep surprising us with phenomena that challenge our understanding. The nuclear symmetry energy, the energy cost of converting protons to neutrons, plays a crucial role in neutron star structure, but is poorly constrained by Earth experiments. In terrestrial nuclei, we deal with roughly equal numbers of protons and neutrons, but neutron stars are about 95% neutrons, probing the symmetry energy in regimes no laboratory can reach. Recent PREX 2 results at Jefferson Lab measuring the neutron skin thickness of lead-208 provide constraints that directly impact our understanding of neutron star crusts. Heavy ion collisions at facilities like GSI in Germany and Riken in Japan attempt to recreate neutron star densities for microseconds. By smashing gold or uranium nuclei together, we create hot, dense matter that briefly reaches nuclear saturation density. But these collisions produce hot matter, while neutron star cores are relatively cold. The equation of state at high density but low temperature remains largely terra incognita. The NICE mission has revolutionized our ability to probe neutron star structure. By timing X-ray pulses with microsecond precision, NICE measures neutron star masses and radii simultaneously. The first results for PSR J0030+0451 revealed a radius of about 13 kilometers for a 1.4 solar mass star, larger than many theories predicted. This single measurement eliminated numerous proposed equations of state. Future missions promise even greater insights. The Enhanced X-ray Timing and Polarimetry Mission, EXTP, led by China with European participation, will measure neutron star radii to within hundreds of meters. The Spectroscopic Time-Resolving Observatory for Broadband Energy X-rays, STROBE-X, would detect oscillations in the kilohertz range, probing the deepest interior regions. Gravitational wave astronomy has opened an entirely new window. Advanced LIGO and Virgo can measure the tidal deformability of neutron stars during the final orbits before merger. This deformability depends directly on the equation of state. Softer matter deforms more easily. The GW170817 event constrained the radius of a 1.4 solar mass neutron star to between 10.5 and 13.3 kilometers. Third-generation gravitational wave detectors like the Einstein telescope and Cosmic Explorer will detect neutron star mergers throughout the observable universe. With thousands of events, we'll map the mass-radius relation precisely, potentially discovering phase transitions or exotic matter through discontinuities in this relation. Neutron stars test general relativity in the strong field regime, where corrections might appear. Alternative theories of gravity make different predictions for neutron star properties. Scalar tensor theories predict spontaneous scalarization, the growth of scalar fields above critical compactness. The existence of two solar mass neutron stars already rules out many alternative gravity theories. The double pulsar system continues to provide the most stringent tests. After 16 years of timing, it has verified general relativity to better than 0.05% in the strong field regime. The system tests multiple relativistic effects simultaneously: orbital decay from gravitational wave emission, Shapiro delay as pulses pass through the companion's gravitational field, and geodetic precession of the spin axes. Quantum chromodynamics at high density remains one of the biggest challenges in physics. The QCD phase diagram showing phases of matter as functions of temperature and density is mostly unexplored. Neutron stars probe the cold, dense region inaccessible to particle accelerators. Whether quark matter exists in neutron star cores would reveal fundamental properties of the strong force. The MIT Bag model and Nambu-Jonah-Lacinio model make different predictions for quark matter properties. Some predict a strong first-order phase transition, creating mixed phases of hadronic and quark matter. Others suggest a smooth crossover. Gravitational wave observations of the post-merger signal could detect the phase transition through its effect on the oscillation frequencies. Superfluidity and superconductivity in neutron stars probe quantum many-body physics at densities where theoretical calculations are uncertain. The pairing gaps, energy scales for Cooper pair formation, depend sensitively on nuclear forces. Observations of neutron star cooling and pulsar glitches constrain these gaps, providing information about dense matter inaccessible to terrestrial experiments. Transport properties like viscosity and thermal conductivity affect neutron star dynamics. The R-mode instability depends on bulk viscosity, which is determined by weak interaction rates at high density. The damping of neutron star oscillations, potentially observable in gravitational waves, directly probes these transport coefficients in regimes where theory is uncertain. Magnetohydrodynamics in neutron stars involves magnetic fields millions of times stronger than anything we can create. The quantum critical field of 4.4 times 10 to the 13 Gauss, where quantum effects dominate, is exceeded in magnetars. Vacuum birefringence, photon splitting, and other exotic quantum electrodynamics effects become important, turning magnetars into QED laboratories. The origin of neutron star magnetic fields remains mysterious. Fossil fields from the progenitor star, amplified by flux conservation during collapse, can't explain the strongest magnetar fields. Dynamo action during the proto-neutron star phase might generate fields, but the physics of dynamos in degenerate matter is poorly understood. Each new magnetar discovery adds constraints to formation theories. Fast radio bursts, if they originate from magnetars as recent observations suggest, probe physics at the intersection of extreme gravity and magnetism. The coherent emission mechanism required to produce such bright radio bursts remains unknown. Proposals range from relativistic plasma instabilities to quantum vacuum breakdown, each revealing different aspects of extreme physics. Asteroseismology of neutron stars, studying their oscillation modes, promises to probe the deep interior. Each mode samples different regions, creating a form of tomography. The F-mode frequency depends on average density, P modes probe the envelope, and G modes are sensitive to composition gradients. Future detection of these modes in gravitational waves would revolutionize our understanding. The maximum mass of neutron stars encodes the equation of state at the highest densities. The discovery of PSR J0740 plus Sixtuno at 2.17 solar masses eliminates all equations of state that predict lower maximum masses. Each new massive neutron star discovery further constrains the properties of ultra-dense matter, narrowing the possibilities for exotic phases. As we emerge from our journey through the gravitational heart of a neutron star, it's time to reflect on what these cosmic monsters teach us about our universe and our place within it. We've traveled from the surface, where gravity is 200 billion times stronger than Earth's, through layers of matter in states that shouldn't exist, to cores where our physics equations break down and new theories await discovery. But the most profound lesson isn't about gravity or exotic matter. It's about the incredible universe we inhabit and our remarkable ability to understand it. Think about what we've accomplished as a species. We've never visited a neutron star. The nearest one is hundreds of light years away. We can't create neutron star conditions in any laboratory. Yet through careful observation, mathematical brilliance, and relentless curiosity, we've peered inside these objects and mapped their structure. We've used gravitational waves, ripples in spacetime itself, to weigh and measure objects that would destroy us instantly if we approached them. Every neutron star in the universe is a memorial to stellar death and a laboratory for extreme physics. The atoms in your body, the carbon in your DNA, the iron in your blood, the calcium in your bones, were created in massive stars that ended their lives in the same supernova explosions that birth neutron stars. In a very real sense, neutron stars are our cosmic siblings, born from the same stellar catastrophes that seeded space with the elements of life. The discovery of gravitational waves from merging neutron stars connects us even more intimately to these extreme objects. The gold in your jewelry, the platinum in your catalytic converter, the uranium that powers nuclear reactors, all were forged in the milliseconds when neutron stars collided, their extreme gravity enabling nuclear processes impossible anywhere else. When you wear a gold ring, you're wearing atoms that experienced gravity billions of times stronger than anything on Earth. The study of neutron stars showcases humanity at its best. Jocelyn Bell Burnell's discovery of pulsars as a graduate student, initially dismissed as little green men signals, revolutionized astronomy. The LIGO collaboration's detection of gravitational waves required thousands of scientists from dozens of countries working together for decades. The NICER mission represents international cooperation to unlock nature's secrets. Science truly is a shared human adventure, but we've also learned humility. Despite all our advances, neutron star cores remain mysterious. We don't know if they contain quark matter, strange matter, or something even more exotic. We can't predict exactly when a pulsar will glitch or when a magnetar will flare. The equation of state at the highest densities remains uncertain. These objects remind us that the universe still holds secrets, that there's still so much to discover. The future of neutron star science is breathtaking. The square kilometer array will discover tens of thousands of new pulsars, including systems that test general relativity in new ways. Next-generation gravitational wave detectors will observe neutron star mergers throughout the universe, mapping the equation of state with exquisite precision. New X-ray missions will measure masses and radii to unprecedented accuracy. Perhaps most excitingly, multi-messenger astronomy, combining gravitational waves, electromagnetic signals, and neutrinos, will reveal neutron stars in their full glory. Each merger will be observed by dozens of telescopes across the electromagnetic spectrum, gravitational wave detectors on Earth and in space, and neutrino observatories buried deep underground. We'll watch in real time as extreme gravity creates and destroys matter in ways that challenge our understanding. The philosophical implications of neutron stars are profound. They show us that the universe creates conditions far beyond human experience or intuition. On Earth, we deal with gravity so weak that we can jump. Inside neutron stars, gravity is so strong that space and time themselves are warped beyond recognition. Yet the same Einstein equations that describe GPS satellites orbiting Earth also describe these gravitational monsters. The universe follows mathematical laws of stunning beauty and universality. Neutron stars also remind us of our cosmic insignificance and significance simultaneously. Yes, we're tiny creatures on a small planet orbiting an ordinary star. But we're also the universe's way of understanding itself. Through us, the cosmos has developed eyes to see, minds to comprehend, and hearts to appreciate the beauty of existence. Every neutron star we study is the universe learning about its own extremes. The diversity of neutron stars, from millisecond pulsars spinning faster than blender blades to magnetars with fields that would rip us apart atom by atom, shows that the universe is far more creative than our imaginations. Nature doesn't just create one type of collapsed star, but a whole zoo of exotic objects, each teaching us something new about physics. This diversity gives us hope that the universe holds countless more surprises. Looking at neutron stars also puts our earthly concerns in perspective. Inside these objects, matter is crushed beyond recognition, time slows to a crawl, and gravity reigns supreme. Yet they're stable, some rotating with the precision of atomic clocks for millions of years. If the universe can create such extreme yet ordered systems, perhaps there's hope for stability and order in our own chaotic world. The quest to understand neutron stars exemplifies why we do science. Not for practical applications, we'll never mine neutron stars or use them for power. We study them because we're curious, because they're there, because understanding the universe is what makes us human. Every equation solved, every observation made, every theory tested adds to the grand edifice of human knowledge. As you go forward from this journey, remember that you're connected to neutron stars in ways both literal and profound. The atoms in your body have experienced stellar gravity. The gold in your electronics was forged in neutron star collisions. The GPS in your phone works because we understand relativistic gravity. You are part of the cosmic story that includes these gravitational monsters. The next time you look at the night sky, know that among those points of light are neutron stars, cosmic laboratories where gravity pushes the universe to its limits. Each one is a natural experiment in extreme physics, a monument to stellar death, and a forge for the elements of life. They're out there right now, spinning in the darkness, warping space-time and waiting for us to unlock their remaining secrets. We may never visit a neutron star, but we don't need to. Through the power of human intellect and imagination, we've journeyed to their cores and back. We've felt the crushing grip of gravity 200 billion times Earth's, witnessed matter in states that challenge our equations, and emerged with a deeper appreciation for the cosmos we inhabit. This is the magic of science. It transports us to impossible places and returns us home transformed. Neutron stars teach us that the universe is far stranger, far more extreme, and far more beautiful than our ancestors could have imagined. They show us that gravity, the humble force that keeps our feet on the ground, becomes a cosmic sculptor capable of crushing matter into unimaginable states. They remind us that we've only begun to explore the possibilities of existence. The journey continues, and the universe waits with infinite patience to reveal its next secret to those curious enough to seek it. If you made this far, please consider subscribing to the channel and giving a thumbs up. Your support is my biggest fuel to keep my journey on YouTube And if you enjoyed this video, I am sure you will love this other on the left side of the screen. Does gravity really travel faster than the speed of light? In this video, learn how gravitational waves, black hole collisions, and neutron star mergers have finally revealed that gravity travels at the same speed as light. Explore how LIGO and Virgo's discoveries confirmed Einstein's predictions, why the speed of gravity preserves causality, and much more. See you there.